Welcome everybody to today's talk within the Design++ speaker series provided to you by the Design++ initiative of ETH in Zurich. My name is Michael Kraus and I'm happy to be your host today. It is my special pleasure to kick off this spring semester and welcome also our guests and lecturers of today, Professor Dr. Jens Schneider and Dr. Philipp Rosendahl from TU Darmstadt. Before I introduce you to our speakers and their talk, let me shortly provide some background information on Design++ and the speaker series. The Design++ speaker series is a recurring event where we will provide information to upcoming events in due time via email, our homepage, or even the YouTube channel. You can find updates on the speaker dates, the speakers themselves, and the topics of the talk of this spring semester on our homepage. If you want, you can also subscribe to our calendar to automatically import the invitations to those events. You are also warmly invited to have a look at the previous presentations, which we will host on our YouTube channel, and the link can be found here. At the moment, Design++ consists of a group of professorships from architecture, civil engineering, and computer sciences here at ETH Zurich. And for the running business, there is a team of 3 leading postdocs responsible for operating the immersive design lab, together with some research and teaching activities. A growing number of scientists and chairs and professorships is associated to us. So in case you're interested in the future of connecting AI, machine learning, and extended reality with the AEC industry, just reach out to us. We are more than happy to discuss further ideas or projects with you. Having said that on the background of Design++ and the speaker series, now let me introduce to you our speakers of today, Professor Jens Schneider and Dr. Philipp Rosendahl, who are joining us from TU Darmstadt, as said before. I was informed that the third presenter, Mr. Costanzi, is unfortunately not available today. Professor Schneider currently holds the professorship for structural analysis, and since 2020, he is also Vice President for Industry Transfer and Internationalization at the Technical University of Darmstadt. Dr. Rosendahl is currently working as head of the Generative Design Lab at TU Darmstadt and is also co-founder of the startup company 2FI, which aims at improving skier safety in the backcountry for transferring scientific advances into practice. The talk today is entitled Generative Structural Design and Additive Fabrication. And the abstract for that I will shortly provide to you. We are witnessing a time when 3D printing has matured from a hobbyist and prototyping tool to a technology that promises to disrupt entire industries in and around the built environment. The developments in additive manufacturing are transforming architecture and design as much as they affect engineering and constructions. Additive manufacturing technologies now enable mass customization, but require a particular approach to design and engineering. While traditional industry manufacturing technologies, such as milling and casting, are well standardized, and a multiplicity of design guidelines and standardized best practices exist, the rapid development of additive manufacturing has outpaced the developments of anything comparable. Surface finishes and geometric tolerances may differ purely due to the positioning and orientation of parts produced by layering. Often an excessive amount of support material is used, and many iterations are required to gain a satisfactory results. The talk today explores these and other implications of engineering for generative structural design and additive fabrication. With that said, I would also refer you to the homepage of our speakers of today. And I will provide this and other background information on our YouTube homepage. And with no further words from my side, I would now hand over to Jens and Philipp. So the stage is yours.
Thank you. Thank you very much, Michael. I hope it's good for the mic. Is it fine for everybody having a mic? Okay.
Yes.
Yeah, thanks first of all, and thank you very much for the kind invitation. Of course, it's an honor for us to speak at ETH in Zurich, and I think it's very good that you have this transdisciplinary group also which very much fits to also our values that only interdisciplinary research and interdisciplinary approaches can really solve many of the problems of today's challenges. And so I think it's also very valuable that we have that viable this exchange today. So our talk is about generative structural design and additive fabrication. And Philip will just show the next slide, where we split it up a little bit to give you information about, first of all, our institute, which consists of different groups. And today, the most important group in today's talk, of course, is our Generative Design Lab. Philip is head of this Generative Design Lab, and we have other groups in structural dynamics, in energy efficient construction, in glass and in paper construction. And you see just from that slide that we have a little bit allocated the different topics to different postdocs and PhDs together with Uli Knag, who is also part of the team, of course. The members of the Generative Design Lab are presented here. So we dedicated a little bit towards the different materials. And I've just to say from the very beginning, although it's about civil engineering, we are not talking about concrete today. So concrete is not our topic. There's a lot of things going on into concrete, but we are not expert in concrete. And I'm also really happy that many things happen there, but this is now not our expertise. We are more in the other materials. Next slide, please. So we are working on clay, we are working on steel, we are working also on polymers or plastics in a certain context of the glass also, because glass always goes together with polymers in the end. And we are talking on paper and we are talking about glass. So in our group, we have, like I explained before, dedicated the different groups a little bit to the topics I showed you. We also prepared in the preparation of today's talk. I was really impressed also by your design plus vision on the right hand side, where you have different aspects that are your goals and how you want to do it. And we try to circle around a little bit, Philip, if you just click. So we think that our today's talk has some links to structural ingenuity, to fabrication aware design, to innovative design, and to a certain extent also to acoustics. This is why I just wanted to briefly introduce that, that you see where we are going today. And I start with the general aspects of generative design in structural engineering, and then Philip will go over through the different materials. And we were thinking that after each of these different blocks, we can have a little discussion, because in the Zoom environment, talks that are too long, as our experience, you get a little bit bored, and it's good to have some more interaction after a certain time. So the audience typically needs a little bit more change of methods within the talks. That's why we split it up into 4 different blocks, and I will start with the first one. So first of all, I want to talk about scale. And I think this is important in civil engineering and architecture, because we are talking today about scale. We are working from the micrometer to the millimeter, the centimeter, decimeter to the meter, and also another scale we typically don't mention, but it's very often used. It's the hectometer, and then the kilometer. So you see that this scales already are a big difference, and I will come to that in the next few minutes. We have issues on imperfections and in the general aspects of generative design in structural engineering. Now also we have more chances in topology optimization. We can have new geometries. We can have different material properties that are influenced by the process itself and by the imperfections. We can introduce functionally graded materials. We can do weight reduction driven by additive manufacturing, and we have a new chance of design in the loop. And the next few slides, I want to just introduce this with one project where I was personally involved in. And first of all, you might think, okay, this has nothing to do with generative design. It's true, but I want to show that the scale effect is something we have to consider when we are talking about generative design in structural engineering. You see, this is the Mont Saint-Michel is a little island in France next to the Normandy coast. And when we zoom in and also zoom more in, I was personally involved in the design of that bridge. And you see that bridge already has a length of 800 meters. And this is, of course, something you will never print in one room. But the question is, in the next slide, how this bridge and parts of this bridge, of course, in the future might be printed. What is the benefit of that, and how we can introduce the benefits of generative design here? Because I think there are chances and there are things that we can consider, but we still have to keep in mind that typically the objects that we are talking about in civil and engineering architecture have that large scale. If you look at the drawings of such a bridge, for example, you see here, this is all in the millimeter scale, of course, the numbers that you see here. But in the end, some of the parts, of course, might be printed in the future. And you see some of the parts here, especially when it comes to welding. Yeah? Then suddenly we have a chance. And this is also one of the aspects we are talking about. For example, it seems very, very simple and kind of not really logical from the first glance that we print such simple hooks. But in the end, if you consider that the element behind it, so the steel profile itself very often is already laser welded, and that then in the arc welding that we can do, we can use the same process that already exists, and we don't have to do other process steps in between. This also already becomes relevant in the construction industry. Next, please. Another example I want to give is a project where we did the structural design for the glass. You see that macro bionic sculpture, of course, is only, let's say, only because of aesthetics here in that point. And this object is 17 years old now already. And if we look then closer into the detailing of such a structure, next please, you see that suddenly when it comes to detailing on the left-hand side, when you have to connect the glass elements, like this is insulating glass, to the supporting structure, which in this case was just a pre-stressed rod that you see in the left top picture where you have the little black square. So the connections there, if you look at these connections, you can imagine that parts of this, of course, very often can be printed when it comes to the question that we have individual design and not such a very, very straightforward plane elements. For example, when it comes to curved elements already, this is an issue. Another issue we have to consider in the civil engineering world is, of course, imperfections. So we have material imperfections, like on the top left, where we see this nickel sulfide inclusion in the glass, which has only a very small size, but when it comes to phase change, it will break the glass from inside. So this is a big issue. And on the other hand, we have these issues that, of course, our ideal geometry from CAD, in the end, when it's printed, doesn't really appear to be exactly the same. Also, you see on the right-hand side an example from Chris Borg, when he did the steel printing, you see we have some issues sometimes. And this has to be considered. And this, of course, also is a problem, because the big issue is then how can we assure a certain quality and how can we guarantee that quality? Because in civil engineering, we're typically talking about 25 to 50 to 100 years of lifetime. And this is also something which is different than in other disciplines. And this is why I think it's important. Next slide, next please. Of course, additive manufacturing enables topology optimization in a way that we could not envisage some 20, 30 years ago. On the right-hand side, for example, if you again have that little element from a machine, when you see the original, then you have a milled and then a printed example. There's a lot of room to have weight reduction and material reduction, which supports sustainability in the end. And I think here is a big chance that we can have that technologies, like, for example, introduced in the built environment much more, because of also the very efficient use of the material in the end. I think this is something that we couldn't do without additive manufacturing. Next, please. Of course, it also enables new geometries. And I think this is one of the key things always why AM is seen to be a future thing, that we can do something that we couldn't before because it was just too complex. If you see, for example, on the right-hand side, that little dices that consist of a framework, just struts and ties, but in that very small size, which can be used to fill a volume. Something like this, for example, is used already in cars from Porsche. And you see that there's many opportunities, of course, to have weight reduction through that new technology, and we can use that also more in the civil environment. Next, please. Of course, the process dependence of material properties is a big issue, because you see on the left-hand side, for example, here the printing that was done was with a contour hedge mix, where you try to have the laser in the powder bed only moved horizontally, and then you see that you have certain issues with the final form here. And if you go for the hedge only, you see it looks even worse. And if you go for the contour only here, it's much better result. So the question how you do the printing has a big impact in the end on the structural integrity and the imperfections. And in the end, of course, also the material properties. This is also shown on the right-hand side in the wide arch additive manufacturing that is done here by Chris. You see different ways to do the individual points, and then suddenly you have different material properties, of course. And this also leads to other problems. Next, please. That we can, let's say, turn around, because we have the possibility now to use the different ways of the printing also to have functionally graded materials, where we have different ways to have such foam type structures being functionally graded. And this is also a big benefit in the future that can be used more to be able to react to certain loads on a structure. And I think there's more room also finally to the design in the loop, so that using new technology also of having the technologies from today's photogrammetry, we can have the as-built system that is already existing, for example, on an existing structure, to be scanned, and then the data being transferred, and then the robot itself then prints exactly where you need it and to the size you need it. And this design in the loop, in the end, is something I think can really change the whole environment in the built environment, especially for the existing buildings and the retrofit, where you don't get some parts and you have to otherwise mill them very intensively, and this is a lot of effort. So I think the design in the loop is also something really can be a good game changer in the future. So this is just a brief introduction of some of the issues from our perspective in the built environment. And I would be happy to discuss with you any questions or remarks now for the first part, and then Philip can continue.
So let's talk about clay and the additive manufacturing of clay. And the particular example that I want to show today is a so-called nesting brick. Ceramic materials, you may know that, are among the oldest building materials that mankind has used. And even the additive manufacturing is older than one might think. The pictures that I'm showing here are from the 1930s, where William Herschel has already patented his machine for building walls. This machine is, of course, much simpler, yet remarkably close to today's concrete extruders. And even back then, he built entire houses with this semi-automated process. Now, talking about clay, about 30% of newly constructed residential buildings, at least in Germany, are brickwork, and the customary extrusion process yields relatively cheap products, but of course they're uniform. So anything custom made, anything customized is a labor-intense process and hence rather expensive. And that's where a customization-driven demand for additive technologies comes into play. To give a brief overview of the state of the art of clay 3D printing, I want to show this. It's actually only a part of this table from a review article that my colleague Alexander Wolf has compiled, and he collected all these different projects that have been done with 3D printed clay. And you see different kinds of applications. There are shading systems shown here, for example. We have heat exchange pipes. We have projects that are solely for architectural purposes, but also coral habitats for life forms. So very diverse. There's a lot of activity. And yeah, you see that customization always plays a role in these examples. And if this gets your attention, I really urge you to read this excellent review article. It's very interesting on this topic. Now, a special application of printed ceramics, and that's what I wanted to discuss today, originates from the following motivation. Construction measures very often cause some kind of habitat loss for birds or for bats or other species. And as a result, authorities often require some form of compensation for this habitat loss. Of course, we can do this in the form of nesting facilities for birds, for instance. However, these exterior nesting boxes, as shown here, are really visually impairing the appearance of the facade. And that's why they're equally unpopular with the building owners and with the habitants. A solution to this can then be a so-called nesting brick. A nesting brick looks like a customary brick and can be included into the facade, but it has openings for birds to enter the brick and to nest inside. And this example that I'm showing here is from a German manufacturer, Hagemeister. They're producing these kinds of bricks completely manually. You see they start with a green product, and then carve out the cavity, screw front parts onto it and everything. It's slow. The process has a yield of less than 100 units per year. And even worse for this kind of manufacturer is that the next generation of trained ceramic technicians that they would need to continue the fabrication of these pieces is nowhere to be found. So they have a massive shortage of skilled labor. And that's exactly where additive manufacturing can address a number of pain points. One, it of course holds the potential to drastically increase the yield of this kind of product, and it can address the shortage of skilled labor that is needed in this case. Now, how do we do this at the Generative Design Lab at TU Darmstadt? In our case, we use a 6-axis industrial robot that is equipped with an extruder head. And with this setup, we have experimented with different kind of printed bricks. For instance, here, we experimented with functionalized bricks that seamlessly integrate into traditional brickwork facades. And this example explores a free-form outer contour and a custom infill pattern in this case. Jens promised that we touch the aspect of acoustics. This is an example of the acoustic experimentation. So we have the typical extruded shape of a brick, and then we experimented with different kind of pattern to see how that changes the acoustic and the thermal performance of these bricks. Of course, as typical for additive manufacturing, the process itself has a tremendous impact on the print quality and the final product. And in particular, in extrusion-based processes, the material that is printed in corners is crucial, because if we print with a constant volume rate, we will find excess materials in these corners. So we need a software design, a software control that controls the process in a way that reduces the volume rate in corners to have repetitive or reproducible surface finishes in the corners. And that's shown here. In this example, we've experimented with the scales that we're capable of printing. And you can already see this little entrance that we've printed here, a hole in the wall of the brick that will, of course, be needed for the bird to enter the brick. And the challenging part is here that we have to print overhanging parts. A hole always requires a ceiling, a roof, or something. And in this case, it already worked quite well. Even more so, even more challenging is the printing of cavities, because obviously printing into the air with no support is a problem for all kinds of 3D printing processes. And for this clay printing process, our solution was using disconnected support material that after the printing process can just be removed easily. You can, with your hand, you can break it off the brick, and that way we're capable of printing cavities. And with these two examples, that's basically the ingredients that we will need to semi-automate or fully automate the production of nesting bricks, and then in the future provide products that seamlessly integrate into existing facades or newly built facades and provide habitat for birds and bats. And with this little example, I would like to open this block for the discussion. And let's talk about steel printing. And in this case, my focus will be on mass customization and, of course, often in metals, lightweight design. So for steel printing at scales that are relevant for civil engineering, we use BioArc additive manufacturing at TU Darmstadt. And this process basically employs conventional welding equipment and uses the deposited weld material to build up structures additively. Big plus of this technology is that it can feature deposition rates of up to 10 kilograms of material per hour. And it's open to a wide range of materials, not just steel that we're using, but also aluminum, titanium, you name it. The material is deposited either continuously, as shown here, or point-wise, as we will see in a later example. The setup that we use at TU Darmstadt is again a 6-axis industrial robot, and this it's equipped with a welding gun. In this picture, you actually see some of the samples that we print in the lab. Now, how can we use it in civil engineering? And I promise that we might come back to the example that we've seen in the first part of this talk, the design in the loop. Here, BioArc additive manufacturing enables mass customization. So imagine you have a substructure that has certain imperfections, maybe even a complex geometry, as shown here. And this will make mounting facade elements, facade panels, as shown on the left, quite challenging because we have to compensate for dislocations, for misalignments. So it's going to be quite labor intense. With a fully digital process, we can simplify the assembly significantly. So we can scan the substructure as illustrated here. Then compare the substructure to a digital model, have a digital process that designs the missing pieces between the supposed location of the connector plates for the facade panels and the substructure. It has to obey certain restrictions. For instance, we don't want to print angles deeper than 25 degrees. Then we print this part on site and assemble directly. We've actually done this as a demonstrator project. I've already skipped to this slide. This is the final facade as you see it with the assembled facade panels. We have printed every single one of these connectors. In the detail, it looks like this. And as you may notice, these connectors are not optimized for lightweight design or for any other, say, structural property. But in this case, they're really just optimized for a fast print. We wanted to have an efficient process as possible, so we can continuously build these up, and there's enough thermal dissipation in this kind of printing process that we can rapidly manufacture these connectors in this case. If you want lightweight structures and not something that's process optimized, but rather mass optimized, then we have to think, in my opinion, lattice structures. And here we would basically harness the unique capabilities that additive manufacturing offers in terms of manufacturing structures that are not accessible with customary or subtractive manufacturing techniques. In this case, this is what I've talked about before. The printing process is discontinuous. So you see the remains of individual dots that we've printed here, and this is nicely illustrated in the video. And notice how we also go discontinuous in different points, and the printer jumps from point to point, and that's because of the thermal management. Again, that's very vital in 3D printing, in additive manufacturing, that we always have to optimize our process for the structural quality. And in wire additive manufacturing, the thermal management is one of the most important aspects that we have to consider to allow for enough heat to dissipate from the structure before we add the next printing point, to avoid thermal deformation and eigenstresses and so on. Designing lightweight structures then requires particularly advanced digital parametric processes. An example is shown here, for instance, to fabricate these lattice-based pavilions that are rendered down here. We optimize the structural design using a fabrication-aware evolutionary optimization algorithm. This solver is fed with the geometric boundaries, the fabrication constraints such as maximum overhangs or the dimensions of the beads that we're able to print, of course with the loading conditions, and is then given our optimization goals such as minimal mass and maximum stiffness. And then we get an output geometry, print this, and can actually put it to the test. Wire additive manufacturing can also be used for the reinforcement of existing steel structures by just welding on top of them. And in our case, we examined the particular case for the reinforcement of very thin sheets. So here we elastically deform sheets as shown on top, and then print on the deformed shape. We print stiffeners on top of the deformed shapes to freeze the deformed shape and produce relatively stiff, very lightweight, and free form, if you will, facade panels, for instance, because we can generate any kind of geometry that we like with the elastic deformation process. Of course, this holds many challenges for engineers. For instance, printing on a curved shape requires the 3D scanning of a shape. We also need a rib layout that is optimized for maximum stiffness, for maximum strength, whatever our goal might be. And this needs to be brought together to an updated model that has the reinforcement on top, and only then we can start the welding process. And also welding onto thin sheets is an extremely challenging process because, as I said earlier, with additive manufacturing, with this wire arc additive manufacturing process, the thermal management is an issue. So instead of printing a continuous line, as shown in this picture, we might want to break up the lines that we're printing into individual segments, print 1, print 2, print 3, and then 4 and 5 to connect it and to allow for the heat that we bring into the sample to dissipate. Similar with ribs that we print in different locations, we have to break up the structure that we add on top into individual pieces in order to allow for the heat to dissipate. Big advantage of this kind of process is, though, that we not only add our stiffeners, but the detailing comes for free. We can add the connections to the substructure, the connection points to the substructure, printed on top, just like a bolted connection as shown here. So we might think that we even print the entire connection to the substructure in one process. And again, this I'd like to discuss with you.
Then the final stage of the presentation will be in the use case of 3D printed glass. And here our goal is the achievement of stronger structures. Additive manufacturing with glass, this is our vision. This is just renderings of where we would like to get, where we like to end up. In this case, you see a console for stairs to connect transparent glass stairs with a transparent handrail and have the connection completely transparent. On the right-hand side, you see a glass facade where the different glass panels need connectors. And in order to make these connectors structurally powerful and very strong, we'd like to avoid the typical drilling through the glass that is necessary, or the addition of adhesives on top of the glass surface for the connection, because every processing step that you do with the glass, every subtractive processing step that you do with the glass, introduces micro cracks that weaken the overall effective strength of the structure, and 3D printing could really reduce the subtractive operation steps on glass. Here too, let's have a brief look at the state of the art. There are quite some activities on the 3D printing of glass, more than you'd maybe expect. There are companies like Micron 3DP and Swarovski. The MIT has printed a bit larger scale samples. At ETH Zurich, there are activities. Laserzentrum Hannover prints on a laser-based process. The Neptune Lab of KIT and the Uni Freiburg, they have a process. QCell is a Dutch company, and TU Ilmenau also uses a laser-based process. What's common to most of these samples that were shown here, MIT maybe goes a bit bigger than everyone else, but mostly these samples are very small, and in particular the ETH structures here, they're extremely fine and very, very delicate. Now we are in civil engineering, so we would like to translate this to larger scale, something that's applicable to buildings and to the huge glass panes that we use nowadays. And that's where we're going at TU Darmstadt. We've started very, very small. Of course, as everyone else, we've basically started with a handmade process and melted a rod onto a glass pane. Looked like this, or like this, I think is even a bit earlier. Not very delicate structures, but it is proofs of concept that you can put to a test. You can investigate the residual stresses in the connection between the melt-on and the glass pane that is shown below. This is done with photoelasticity methods. We've analyzed the chemical compounds in the transition zone between added structure and the glass pane. We've looked at cracking and how cracks might travel through or along the interfaces of printed structures. And this result is actually really promising, and basically only see how we broke glass, but it shows that this crack, for instance, traveled across the interface, and this one too, and not along the interface, which means that we have a very good connection between the added structure and the base plate. And we've even put this to some load-bearing tests and done this with photoelasticity again to visualize the stress concentrations here. So these are very basic tests, and this gave rise to the motivation to actually print a larger scale 3D printer. It's under construction right now. Unfortunately, I can't show printed samples, but the basic structure is that we have a cavity in the top of the printer that will melt the glass, will extrude it through a nozzle, and then have a heated chamber. This is the heated chamber. You can see it on this side too, where we can control the temperature on the base plate that we're printing on to have a connection at the desired temperature between the melt and the base plate, and of course a motion unit that translates and rotates our sample. With this printer, we're hoping to print large-scale structures. Large scale in this case would mean, I think it's 500 millimeter by 500 millimeters and something like 200 or 300 in height of printable dimensions, and printable onto glass base plate. That's the unique feature that we think where glass 3D printing offers a big potential by connecting different glass pieces. And then again, what we're thinking about doing with this, similar as with the stiffened metal sheets that I've shown before. And here is where we maybe get back to the bird-aware design that birds might see the glass structure, is by printing on a glass plate, either stiffeners in these kind of layouts, in these kind of shapes, maybe something artistic in a free-form pattern that makes a very large glass pane more visible, for instance, to birds, or to do something like done here in concrete to reinforce it with the stress trajectories and just stiffen out the plate massively. different designs that we were thinking about how to connect glass plates with each other. On the left-hand side, you see the conventional connectors, which are either glued on top or drilled through the first glass pane in case of a laminated glass and then connected to it. This is where printed glass might offer different options, where, for instance, the load can be transferred in the actual direction that it is going, and we have less bending. That means less loading on the glass connections here. When we want to stiffen out glass plates, this is the traditional way we're going. We're just adding more layers of a laminate. With printed glass, we can follow the stress trajectories or just be smarter about where we add our material to stiffen out. Then we have insulating glass units, in particular vacuum insulating glass, where a big challenge is the edge connection of the different glass panels. Here we could harness our printing process basically as a welding process, or even in bigger constructions where we need a spacer and a sealant, we could print around the corner and then have much less sealant needed here. One example where we could see it very practically really applied is this glass bridge that was recently built at the University of Pennsylvania with colleagues from their hollow glass units. You see the scale of the bridge, someone's walking past here. And in these bridges, we have these kind of insets, these connectors that connect the different hollow glass units. And if in the future we could print elements like this and make a more direct connection here, we might actually enable glass to be used as structural elements and for people to walk over. And I'd like to close this task with an example that Jens really liked to show. This was in 2002 when they made this glass pool for the expo in Switzerland. And they had these artistic glass columns assembled from individual pieces, very impressive pieces. And he said, if we could print this in the future, that'd be his dream. Thank you.
Cool, very nice. So yeah, especially for me as a former glass person, that's very cool. Final picture. Thank you, Jens and Philip, for this interesting talk and the lively discussion. Your time and efforts are very much appreciated. As I said before, I will upload all information of this talk together with the video to our YouTube homepage. And yeah, especially I want to highlight the next talk in this speaker series, which is delivered by Dr. Romana Rust and me in about 2 weeks. And the talk is concerned with our perspective on augmented intelligence concepts for design in architecture and engineering. So yeah, thanks to all of you again. Stay safe, and we will see you soon.